All right, so let me just pick up where we were at last time. I can't, I just want to summarize a bit, but I can't start from the beginning because that's crazy. We're done with WKB. We're going to finish today. And recall that, it's kind of like a little Russian nesting doll. There's an initial, some work where we work with a wave function that's like e to the I, a function. We assume that the solution looks like that. There's no approximation because if the function can be anything, e to that function can still be anything, and anything can solve anything, like the Schrodinger equation, right? So that's a simple way to put that. Once you start making some approximations, you're going to get, let's say for e greater than b, you're going to get this thing here, where k is a momentum vector, e to the I integral k of x. And don't forget that we used to have a little h bar in that, but that was when we had momentum. So if this was I over h bar, that would be momentum, but we know that k times h is momentum, so I cancel out the h's that way. So I'm only doing that because most people express it this way, but it's kind of not how we derived it. So that's a bit of a pain, but I'm just concerned that if you're looking up things online, which, if you get a little confused on the homework, you might do that, and you're going to see this, and you're going to be like, oh, okay, well, they're calling what I call P a K, where's my H bar? Anyway, so I just want to point that out. Now again, remember the salient features are that it looks just like a free wave, it's just that the wavelengths are just modified in this way. So cool that. We're going to talk about harmonic oscillators today, but we're going to go back to the particle in a box because I got something kind of surprising. Let's, here's the lowest energy solution, but let's look at a very, very high energy solution. So this is the V equals 0 state. Remember, that's a ground state for a harmonic oscillator, and hopefully you remember that. I'm going to look at a very high energy state because, and I'm looking at wave function squared, and it'll look like this. 1, 2, 3, 1, 2, 3. And I just want to remind you some things that we think of. The scale that I'm drawing is kind of arbitrary. I didn't do a very good job with my mirror symmetry, but we think of the potential energy, which is quite high, or something that's stretched out here or compressed this way. The potential energy is quite high, and if you calculate the kinetic energy, you'd find that the potential energy and the kinetic energy are the same right there. The total energy and the potential energy are the same right there. That means it has no kinetic energy, and that's where it normally turns back around. It expands and contracts, and before it contracts, it has to stop. Now that results in a singularity in these coefficients, right? K is 0. It's not moving. Momentum is 0. And that's actually part of having an approximation. Think like, oh, well, how does it get around that? It doesn't. It's an approximation, and that's where it fails. I just want to point that out because we're going to get back to that. So that's just one thing to look out for. Now, before we get to this problem, let's do a model problem, and we're going to go back to particle in a box. And I was kind of rushing this last time. And I'm going to do this with a slightly different symmetry. I'm going to go from 0 to L as opposed from minus A to A. And I know that the ground state is, I always know the normalization is 2 over L. And I always remember that a wave function, a spatial wave function, let's just say it's an X. We're getting to Y and Z later. If it's an X, the wave function actually has units. It has to have the square root, 1 over the square root of space. And that's because when it's squared and integrated, there can't be any units at all. So that's how, it's like, is it L over 2 or 2 over L? I always know it's 2 over L. Because again, it has to have units of nanometers to the minus half. Anyway, so the ground state is sine pi x over L. And you can figure that out. You can just look at this and see that that's what it is. All right, anyway, so I'm cheating. I'm cheating. All right, now what I said last time was that in the WKB, let's see what that approximation does. 1 over the square root of the k vector. And remember that potential energy is constant, so this has got to work. I'm going to have sine A is equal to minus B. I'm actually going to show you how you know that, but again, you can take it for granted that A is equal to minus B, and that means that you know, e to the ix minus e to the minus ix is sine x. All right, so I know it's a sine function, and of course the arguments in the WKB is the integral of kx dx. Okay, now I ended here last time, and I want to point out that you may have seen me kind of get a little bit I started doing that a little bit, and that's because I got a little flummoxed about something. Let me solve the energy. We're going to solve the energy. And I showed you this last time, but then I'm going to I'm not going to do anything wrong. I'm not going to do anything wrong, but I'm going to make a major misinterpretation. And I want to see if you can catch me. Even though I'm not going to do anything wrong, which is kind of damning. And this will be good for you. Because you get used to, well, I'm going to show you some nuances of equations. You'll probably run into all kinds of equations in your statistics stuff, right? And sometimes people write papers with a lot of mathematical analyses, and they don't really tell you how they work. And we're going to run into that here. You're going to run into a weird problem that you don't realize is a problem because you have to have some more experience, right? Okay, now here's the thing. Now I know that the wave function is of course at 0, the wave function is 0, the wave function at L is 0. Okay, so if I want to get the energy, just like the original problem in the more simple form, I apply a boundary condition. So notice what I did here. I'm going to integrate kx. I'm going to use another board here, dx, and I'm going to set that equal to n pi. Of course, I better have limits, and the thing is only defined between 0 and L. So, of course, I'll apply those limits. Now, one reason I want to do this, sorry, here we go. The reason I want to do this exactly is I want to remind you that this is actually really quite easy, 0 to L, and don't forget that K is going to be 2m E minus V, and V is actually 0, so I'm going to do that. I'm just going to say 2me. Okay. Now remember, this is not momentum. This is the K, so that means I have to divide that by h bar. Just a little nuance there. Okay. This is real easy, right? It's got to be, sorry, this has got to be, let me integrate this and I'm going to set it equal to n pi, just like I did up there. Okay, what is this?
X times.
Yeah, it's just x upper minus lower. It's just 2me. Remember that the v isn't there because the v is 0. H bar L is equal to n pi. Therefore, n pi h bar, sorry, over L. Square everything. And then divide by 2m. And that's equal to the energy. And that's exactly correct. That is the particle in the box energy. So they're kind of easy. So, and again, a lot of this is about flexing your math muscles. And also, I'm trying to quiz whether you remembered what I said about 3 minutes ago. There's a problem. What did I do? I did something kind of wrong here. Phenomenologically. Now, the math is correct, but I'm telling you, I am not thinking about this correctly. Let me point this out. why don't we go back to the original form? Not assuming that we know what k is, that a and b, sorry, a and b. I integral kx dx plus b square root of kx e to the minus I integral kx dx. Okay, here's my point. Let me point this out to you here. And to emphasize what I'm saying here, let me decide WKB of X. Okay. Let me point out what's happening here. This is the wave function. Now it should be perfect. It will and it will be. This is what it looks like. It's a function of X and it goes from 0 to L. So imagine I'm doing this in MATLAB. I have to insert X, 0, let's say, we'll make it 1 to 1 nanometer because that's where an electron, we're talking about electrons. Electrons like to live 1 to 1 nanometer. So I plug in 0, 0.1 nanometer, 0.2 nanometer, 0.3 nanometer to 1 nanometer. I don't go further because it's 0. Right? Now look what I did here. This, again, has to be defined for whatever I put in. 0, 0.1, 0.2, 0.3. But then I just made this equal to n pi. I made the argument of sine is equal to n pi. I just set it equal to something. Can I do that? You see what I've done here? If I said that this is n pi, sine is 0. Sine of n pi where n is 1, 1, 2, 3, 4, 5 is 0. I just made this wave function as a function of x uniformly 0 everywhere. Now that absolutely is not right. That is not correct. So it doesn't seem like I can do that, does it? I mean, I absolutely cannot. Yet it worked out. So something's funky. You see, when you get stuff like this, and let's maybe go back to this, you better be able to interpret it right, because obviously I am misunderstanding something. I cannot just say that argument is n pi. Now, here's one of the solutions. I want to see if you can figure it out, but I want to point out that you get the energies from boundary conditions, right? You get it from a boundary condition. Now, therefore, that psi of WKB, x is equal to what? I have to make x equal to something to make the argument of sine equal to something, right? I forced it to be 0. I forced the wave function to be 0, and the only way to do that is to make sine the argument of sine of n pi. Therefore, I'm talking about at x equals what?
0 or L.
L. Let's say it's L. Okay. All right. Now here's the thing. When you plug in an x, now you got to think about where does it actually go. Now it looks like this guy's okay. This guy's okay. We know what k is. It's this right here. There's actually no x in it in this case, right? Because it's a flat potential. It's fine. So this is actually just a number. It's just 2m square root of 2m e over h bar. So this is cool. Now the only other x is here. Now, do I plug in x of L? Do I say, when I'm mapping this, when I'm drawing this wave function in MATLAB, and I'm saying x is 0, 0.1, 0.2, 0.3, is that going into here? Am I just saying k of 0, k of 0.1, k of 0.2, is that what's going on? Is this and this the same thing? Cannot be. It's impossible. Those cannot be the same thing, because then what the hell is this? Right? If you're giving this, if this, argument, let's make it L, and you just put that, if you put an L in there, if you put in whatever this is, you put it in there, what the hell is the point of integrating it? Right? It's just a number. If this is just a number, then it's just that number times delta x. Now, that actually turns out to be the case in the harmonic, in the box. In the particle in the box, that actually turns out to be true, but that's a special case. So again, this x and this x are actually not the same x. And that now, and I'm writing this out by the way, when you look on the internet or even your textbook, this is how you see it. But there's a subtlety. That is not the same x. The way you should actually do it, by the way, is like this. Give it a little dash, and the x a little dash, and you're going from x naught to x, right? It's actually the upper limit of that integral. I'll tell you what, make it real easy. Let's make x naught equal to 0. Okay, now let me point this out. Let's do an indefinite integral, and let's just do x. Okay, and that's 1/2 x squared, right? We agree on that. Now, tell me this. What I contend is that there really are no indefinite integrals in what we're doing. I contend that this is what we're really doing, right? Now, so I've taken this thing and I've done the integral, but now I apply the limits. What do I get? The same thing. It just doesn't have a little dash by it anymore, right? But does that mean anything? Yes, it does, because this is actually how you do this. That's actually how you do these integrals, right? So, careful. Because again, the way I wrote this out is how you often see it. And actually, I did find, as I Googled all this stuff, all right? I Googled a lot of this lecture. I found one handout from a physics group that actually did it right, where they put a little dash on these x's so that you knew this x and this x were not the same. But that's rare. I found one out of like 20 documents that did it right. And I know it's right because of all the reasons I just said. I didn't need to find that one document out of 20 to know it was right. I had already figured it out. I was glad I found that document because it confirmed it was right. And those other 19 people are actually wrong. Not wrong, it's just that they expect a level of sophistication out of you that, fine, but someone has to show you at some point, right? Or you have to figure it out. Okay, now let's go back to the problem we had and let's redo it. Now let me do, so now one way to look at this. Now let's think about putting it into MATLAB and putting numbers in, 0, 0.1, 0.2, 0.3, and thinking about how the wave function is created. Okay, let's start at 0. Okay, again, this actually happens to be a number. It's 1 over the square root of 2me, blah, 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 over h bar. And this is integrated. This is just a reference point. You could actually literally pick any point, but 0 is fine. So this ends up being e to the. If I'm gonna just, now again, it's completely arbitrary. It's fine, and it always works out to be the same. That's a little counterintuitive, but trust me on that. From 0 to the upper limit is what? Again, I'm trying to create the first data point. And I'm going to try to do this. Again, I'm using MATLAB. So I'm trying to recreate the wave function in MATLAB. I'm using definitive numbers. So my first x is 0. Again, that's a number. I've got 0 to what? To 0. I'm integrating 0 to 0. What's that? It'd be 0. Right? There's no, remember, all right, here's a way to think of that. Integrals are areas on the curves. What happens when the width is 0? There's no area. Okay, so this first data point I've got, what's e to the 0?
1e.
Yeah. Right, e to I0 is also 1. So I've got basically a plus b equal to 0. In k, whatever. So at x equals 0, a is what relationship to b? Huh? Minus b. Right? It has to be a is minus b or the wave function is not 0, which is the boundary condition. Right, so that's how I know it's actually a sine function. Okay, now let's go to the other extreme. A is equal to L. And we already know it's a sine function. We already know that it's actually 0 this is what I was actually doing. This is what I was actually doing. I wasn't doing the wave function at x, I was doing the wave function at L. And that's why my upper limit is L here on the integration of the k vector. And that's why it has to be n pi, because at x, at the wave function at the right half, at L, the damn thing has to be back to 0 because of the tension. That's why I can use this upper limit of L, and it integrates to the correct energy. Anyway, kind of neat, right? Oh, that's kind of cool, right? Because here's the thing. You often run into this situation where, again, I write this out. Notice how I was just chugging along and chugging along and chugging along. And I thought, like, this is why I was kind of stammering last class, because I realized when I did this, I was like, no, wait a minute, why am I putting an L here? I'm like, I'm setting this equal to 0, but I had an X here, and I'm like, wait, it's not 0 everywhere. So that's why I got a little stammering, and I realized I was kind of not thinking about this right. And then I do actually know this, and then I remembered to get the lecture you just saw. Anyway, so look out when you're doing equations, because you run into stuff like that. And no one's going to necessarily tell you about the subtleties. You just simply have to have a lot of sophistication and experience to recognize those kinds of pitfalls. But that's why you're here, right? That's why you take this class. So, PChem here, our point is for you to learn quantum and to think quantum mechanically, and that's our main goal. But we value mathematical chops, right? We value mathematical ability and prowess, and so we need to do some of that too. Okay, next one is a harmonic oscillator. And I want to just point out that, now this we're just going to blow through. You often see the potential written this way, Hooke's law. Well, Hooke's law is the forces minus the how far it's stretched, and then you integrate that to get the energy. So you end up with 1/2 minus kf, that's the spring constant, x squared. Okay, now it turns out that the angular frequency is the square root of kf over m. M might be like a reduced mass. If this is like a paddle ball, and so you can assume that the paddle is like infinitely massive and the ball is the mass, then this is fine. If it's like an H2, then it's a reduced mass. So I'm not going to indicate it beyond that. Now here's my point. When you get to higher level stuff, you never see it done this way. It's just we often express things in ways that are unfamiliar for that purpose, to make outsiders outsiders, to make it inaccessible to outsiders. So I want to point out that you often see it written this way. 1/2 m frequency squared x squared. You actually almost always see it done this way. Once you get into higher level PChem, math, quantum, yada, yada, yada. Okay, now remember, like the particle in a box, we're going to be integrating from over some kind of limit, from where the wave function starts to where it ends, and we're going to be setting that equal to some function of pi for the same reason we did the particle in a box. So we're going to get the energy. We assume we can get the wave functions. Wave functions are actually just stepping stones on our way to energy. So harmonic oscillator, WKB energy. I just definitely want to point this out. Okay, now, as I've been blabbering about the limits of integration, the limits of integration here are going to be the turning points, which I've already defined. It's where your momentum goes to 0 and the wave function blows up. So we're gonna define those as our turning points, and so that's where this is equal to E. Now notice that you're going to get 2 turning points, and these are positions. I've got x squared, so if I've got x squared, I'm going to have 2 possible turning points. There's an upper, and you have to do this on your homework too. 2e over, and then lower is just minus that. Because of course when you square a minus sign, it's still positive. If you square a positive sign, it's still positive. So there you go. Okay. Now, this is where it gets a little bit funky. All right, let me now the energy, calculate the energy, and we're going to do that by integrating from our lower turning point. And again, I want to emphasize that this is for the same reason that we did harmonic oscillator. 2e m angular frequency squared plus, on the bottom is minus, plus x minus x, 1 over h bar, square root of 2m, E minus the potential energy. And now we're doing something a bit more sophisticated, m angular frequency x squared. Okay, so finally we're doing something a little bit more sophisticated. Finally, not the potential truly is not flat. This thing, I do not, parenthesis, so the world will blow up. That X does not look good. It has to be looking good. Looking X. Now we're doing something more sophisticated, but I have no, I mean, I'm not worried about the limits. I have no idea how to integrate that thing. I don't have a clue. So I did it on a computer. But now, of course, I got to set that equal to something, but here's the thing. It's not n pi. It's n plus a half pi. Now let me try my best to explain that. Okay, what happens is, before, in the particle in a box, you truly go from 0 to L. That's it. The wave function, you have clear boundary conditions, especially the one at L. That's the one that matters. The wave function is definitely 0 here. That doesn't happen in this SOD. It actually goes past the turning point. Technically, the energy is imaginary at that point, which is nuts. But, I mean, so things stretch more than their kinetic energy allows. They stretch to the point they have imaginary energy. And I don't even know how to imagine that. Anyway. How old am I? Anyway, okay. Now, it turns out that between the fact that you have a singularity in the wave function and the wave function keeps going, physicists who are obsessed with this spent a long time figuring out a solution. And they did that by making all these freaking approximations to the potential energy, and it just did. If you look up the solution on the web, it's 3 pages of algebra. It's hideous. Obviously, 3 pages of algebra is very unpleasant. The end result was not that you go from n pi, that as you go from the left to the right, that you go n pi, you go n plus a half. So you pick up, in their language, you pick up a phase factor. That's the correct language. Okay, anyway, so I don't want to spend 2 lectures doing 3 pages of derivation that I really don't even understand myself, all right? I just accept that this came out of it. And you also see that in your homework. And so, of course, n equals 0, 1, 2, 3 in this case. Let's see here. Okay, then what I did was I got Mathematica to do this because, I mean, damn. Ended up spitting out pi e over the angular frequency is n plus a half. And I think I used a letter D, or nu last time, so I kind of messed with you there. I should have used an N, I guess. So therefore E is n plus 1/2 h bar angular frequency, where n is 0 for the ground state, and on and on and on. Okay, we got lucky. It happened to be exactly right, but I want to point out that this is an approximation, and if you look at harder problems, it will diverge. Like, you can actually do the hydrogen atom with this. I'm not going to do it. You can do the hydrogen atom with this, and it gets close, but it's not perfect. So you notice that I'm kind of cherry picking the problems I'm giving you, because it's like cool when it works out perfectly, but I also want to make sure that you understand this is a semi-classical approximation. It will not always give exact answers. But the most important thing, again, is to think properly about how waves work. particles are true waves, and the wavelength changes based on the potential surface. You've also picked up a bunch of mathematics, and there's value in that too. Now, last bit I want to go over is what physicists, again, just love this stuff. They want to marry it. Tunneling. They do a lot of tunneling phenomenon with this. And this is kind of cool because what I like about this is that it gets you a little bit more mathematics. So nothing wrong with that. But what I found was some tunneling with WKB. You know, when it comes to quantum, the only things you really got to know are like scattering. And tunneling and scattering, I guess they're kind of the same. Tunneling is when you don't scatter, so everything else is, whatever is not tunneling is scattering, I guess. And then the structure of atoms, right? Those are resonances. Resonances, scattering, structure of atoms. That's about all that we ever care about. Okay, now, let's have a potential surface like this, so it's an inverted harmonic oscillator. And our particle is going to go through it. Okay, now we're going to assume that call that x1 and x2. Yeah, I just want to make sure I use the right language here. We're going to assume that energy is less than the potential height, the potential barrier. Call that V naught. Remember, if the energy is greater than V naught, the particle gets over it. So, well, probably gets over it. It's kind of boring. We care more about, it's cooler when the particle should not get through it, when it does not have enough energy, yet it does anyway. So that's the one we want to work on. Okay, in that case, of course, we can still have region 1, and that is going to be A e to the I k x plus b. Oh, what did I put a little plus there for? I don't know why I put a plus there. Minus I kx. Now that's exact because it looks like largely a flat potential surface. Okay, and now we've got region 2. Yeah, it looks like I did not give myself enough room, did I? That'll be let's call that a C wave, square root of kx, e to the minus integral of kappa, so there's no I, and that will be added to a D wave, which of course has e to the plus kappa x dx. And of course now you know how to deal with your, how to read it right, so that your x is really, in here is actually an upper limit of integration. A little subtlety there. Sorry, I just used the board terribly, didn't I? And this would be e to the minus I kx. Shouldn't use E, right? There's two E's now. There's an E for the amplitude, and there's an E for the energy, so that sucks. Anyway, and I'm not going to read any more about it. I'm just going to kind of blow through this because I have tried to find this, but I cannot. So now we're going to analyze this thing for like the amplitude of the E wave. We're just going to use a WKB wave function. That's the idea. And then we'll integrate it from x1 to x2, where x1 is 0. And here's the thing. I cannot find the derivation to this, and I am not smart enough to figure it out on my own, forget it. But I found this. 2, and I want to use the right language. Okay, and then we call this so that's like an angle, right? And again, I'm giving you what I found on the web because I want it to be familiar to you in case you look this up. I guess it's because maybe we're integrating kappa. And again, you can see how I use the limits. Remember, kappa is for when the energy is fully decaying, so that ends up being you know, we normally would have a little I in it, but what we do to get rid of the I is note that E is less than B. So if I switch V and E as I've done just right here, then the I's cancel. Anyway, I hope you remember all that. It was just a little while ago. So anyway, it turns out that this is an extraordinarily well-known expression for tunneling. And if you get into the right type of experiment, you will see this. And so I just wanted to point out that this is where it comes from. It's a WKB thing. You set this problem up if you know how to solve it, which I don't. I'm going to show you an approximation to solve this, so that you kind of get an idea of the physics. I just want you to know this stuff exists, but now I'm going to give you a little bit of an idea how to solve it. And I can do that. Now, I do know how to do this one. I know how to solve it for an approximation to this is e to the minus 2. Again, our function, our phase function, our integrated k function. This guy I can solve for. I know how to do this one. I looked it up. Okay. Now, what we'll do is, I'm going to need a new board. We'll work this. This is going to at times make your head spin a little bit. I understand if you may get a little bit lost. I think I got it. I've been staring at this for a long time. I think I got it, but that doesn't mean that, you know, maybe I'm going to make a mistake. I hope not. But you may have a little bit of a hard time following it. You know, this is why I have videos so you can watch this again and again, assuming I'm not going to screw this up. Okay, and what I'm going to do is I'm going to go back to more familiar language. I'm going to go back to, I want to actually kind of simplify that parabolic barrier. I want to remind you of what these really kind of look like. They look kind of more like this. So there you go. Okay, because I'm going to use this to make some approximations. Now, of course, the WKB is an approximation. We're going to throw some more on there. And let's see, I'm going to go from 0 to A. And again, I probably should be a little bit more careful with my, what I call X1 and X2 and A. I'm kind of blowing this here, so sorry about that. Okay, so number 1. Okay, approximate. When I say number 1, I mean approximation. Here, assume. So now you know it's an approximation. We're going to call wave function in region 2. And we call it X prime. Now I'm going to call it X prime because we know we have to be a little bit more careful about where our X's really are. And that's right here, minus 0 to X prime, k of X, not X prime there, that's different. I could have called that X and then, wait a minute. If I called that an X, that would have been an X, that would have been X prime. Maybe that would have been better. No, anyway. Okay, now there should also be a D wave. Right, there should be a D wave. Screw it. No D wave. Remember, it's an approximation. Excuse me, this is our approximation, no D wave. The idea is that the incoming wave gets used up, it's attenuated, some of it leaks out. Remember, the D wave is the wave that actually reflects off this barrier. So there's a reflection off the first barrier, then there's a reflection off the second anti-barrier. That's kind of weird, right? But you know how if you spray paint something flat, very flat with a flat black paint, you know you can still see yourself in it, right? You know what I mean? It's still, black things are still reflective, even if they, I mean, sometimes they're coated, so of course they're reflective. But if you just get black, flat black spray paint like this, you can kind of look at yourself, right? You know what I mean? That's actually this kind of phenomenon. That's a reflection off this barrier, even though it's like an anti-barrier, right? It's the loss of a barrier. It's really the interface. So that's why we have these D waves, by the way, the scatter back off the anti-barrier, the sudden loss of a barrier. Really, it's just an interface. But we're going to say that it's not there. So that's an approximation. Okay, now the second thing is, and this is not an assumption really, the wave function at 0 has got to be equal to the wave function at 1 at 0. That's continuous, right? That's a normal, the wave function has to be continuous. Okay. Now, what that means is that all the, this integral will integrate to 0. The integral is 0, so e to the 0 is 1. Okay. Let's see. And number 3, the wave function in region, where am I at region 3 at A is equal to the wave function in region 2 at A. Again, continuous. So approximation, and then those are just normal continuous boundary conditions. Okay. All right, now I'm going to write out the answer, and don't throw up. Okay, it's going to be a little confusing. Now this is actually another approximation. It's not a big one, but we're going to say that the amplitude of the region 3 wave, which is just E squared, the amplitude squared, is, the transmission is E squared. Typically it's actually over A squared, which we set equal to 1. That's how we solved those other questions. I don't know if you remember A is the incoming wave. This is basically the same thing as setting B equals to 0. So you assume you don't have any reflective loss off the first barrier. So we're making a lot of approximations here. So note that this is an approximation. Okay. Now, wave function 1, the denominator is the same. Okay, now watch this with the numerator. Note that the amplitude in front has to be equal to the amplitude of wave function 2. The amplitude which is in front in wave function 2 is equal to that of wave function 1. That's because of this and the fact that this is 0 and e to the 0 is 1, because we're at the boundary condition. So again, I'll write it down. The prefactor of wave function 2 is actually wave function 1. That's the prefactor. And again, it's because at 0, the wave functions are equal, and this integral ends up being nothing, ends up being the number 1. If this is nothing, the only thing that's left is what's up front. So I'm writing what's up front. Now I have to do this integral, and I have to do the integral squared. So I'll put a little bracket. E to the minus 0 to A, kappa x dx squared.
It's 5 2 over 5 100.
Huh?
Is 5 2 square or 5 1 both are equal?
Sorry. Yeah, so phi 2 and phi 3.
Yeah.
And, I didn't say that. This is equal to 2, and 2 is equal to 1.
Yeah.
Right, sorry, just, so I did flub it a little bit. So 3 is equal to 2, and 2 is equal to 1. And now the reason that so I explained why this guy works, and how the integral is equal to 0, and e to the 0 is 1. But okay, now let's think about this guy. How do you build wave function 2, right? You take its amplitude, which is wave function 1 at 0, and you integrate across from your starting point to your end point. So wave function 2 times this is wave function 3. It's this. But this says that my prefactor is actually wave function 1. I told you this is such a fucking thing. And this ends up being e to the minus 2 0 to A, kappa x dx, which is the same as that. It's the exact same thing as that right there. same as above. T is e to the minus 2. And again, I'm using the language I found on the internet because it's familiar. Okay, so anyway, I know that this is, I found this a little head spinning when I was writing these notes. Again, I know this is kind of hard. The thing that kills me is that wavefunction 3 has the amplitude of wavefunction 1. This is what really took me a hell of a long time to figure out. And it's just here to here to here to here. That's where that comes from. The integral here doesn't exist because you're integrating from 0 to 0. But the integral does exist when you're talking about 2 to 1. You make 2 turn into 3 by integrating it from 0 to a. And that's the length of the barrier. Once you're at a, wave function 2 is now equal to 3. And that's what makes this happen. Everything is squared, and that's where you get the little 2. The little 2 comes from the square. Okay, anyway, I promised you to on time. If you stare at this for several hours, it will be clear. Short of that little flub I made, I actually, this is technically fully correct. It's weird, but technically fully correct. No, other than these approximations, I think I did this right. So again, just so when you're looking at this and you're getting frustrated, you may at times think, oh, well, maybe I made a typo. There's no 2. That's good thinking, and you should check with me because I am going to do that, but most of the time not. Probably most of the time I won't. So you just got to stare at it longer, which there's a lot of value in that because welcome to grad school. And I got to